All right. Hello again, everyone. So today we're going to be talking about the derivatives of inverse functions. Once again, a little reminder, we are going out of order for these two sections. So we did 3.8 yesterday. That was on implicit differentiation. We're doing 3.7 today. And that's because I'm going off book. I don't really like what the textbook does for 3.7. So I'm doing my own version of derivatives of inverse functions, which honestly is a little bit closer to what derivatives of inverse functions really is compared to what the textbook does. Um, but our version will require us to use implicit differentiation, so we needed to do that first. So if you haven't yet done 3.8, make sure you do that lecture before you view this one. Otherwise, this won't make a whole lot of sense. All right. So before we get into it, we should discuss what it means to be an inverse. So we're going to kind of talk about two different types of derivatives of inverses today. The first is going to be actually taking the inverse of a function and then finding the derivative of the inverse of a function. The second is going to be looking at inverse functions. All right, the difference between that is going to be an inverse function is something like arcsine or arc cosine, where it already is an inverse by construction. And the first one is going to be something like given a function, find the inverse, and then find the derivative. Okay, so a little reminder on how to find an inverse. So we see this line y equals x. All right, so given any function, if you reflect your function over the line y equals x, you get the inverse of that function, given that the domain is satisfied and everything like that. So what that means is if you're given a table, you would flip the x and the y on the table, and that gives you an inverse. If you're given an equation, you would switch all x's with all y's, and that is your inverse function of the equation. All right. In terms of domain and range, just a little side note, I guess, the domain and range get flipped. So of the original function, you'll have the domain and range. Of the inverse function, the range becomes a domain and domain becomes range. All right, so everything, all types of x's become all types of y's, essentially. You just flip everything. All right, so let's talk about the first case that I mentioned, which is how to find the derivative of the inverse of a function. So this isn't going to be like an arc sine or an arc cosine. This is going to be here's a function, find the inverse, and then find the derivative of that inverse. Okay, and again, a little note to find inverse, switch all x's into y's and all y's into x's. And that will just give you your inverse. All right, so here are the steps to actually finding the derivative. First of all, take the inverse. That seems pretty self-explanatory. Second, we're going to find the derivative, and we're going to need to find that using implicit differentiation, because we've now found the inverse, which means that we have x in terms of y instead of y in terms of x. So we will be using implicit differentiation. After that, we're going to be just solving for dy dx using the implicit differentiation techniques we used in the last lecture. So we'll solve for dy dx or y prime if you'd like that instead. This last step is something that we didn't get to do last lecture because it didn't apply. It will apply now. So because in this specific case, we will have y defined explicitly, so we'll be given like y equals some function. And then when we actually take the inverse and solve for it, we'll be left with something in terms of x and y's. Well, in the cases we looked at yesterday, we weren't defined explicitly from the beginning, so we didn't know what our y function was equal to. Well, there was no y function. Here we do have a y function. So once you find your derivative function and you've solved completely, you can take the original function that we started with and just plug that in anywhere you see a y to get every single thing in terms of x. And we will do some examples to kind of show you exactly what I mean by that. But this is a way to make sure that everything is just in terms of x's. All right, let's do an example. All right, so this says find the derivative of the inverse of y equals x plus 2 over x. So because we are looking at the derivative of the inverse, we have to be very careful about the language they give us here. We first need to find the inverse. So let's do that. Inverse. Again, inverse flips all x's with all y's. So this y will become an x, and these two x's will become y. So y plus 2 over y. Now, you could theoretically solve for y. We aren't going to solve all the way. We're just going to change it a little bit. So what we're going to do is we don't want this fraction here. We want to make it look a little bit nicer. So we are going to multiply this to the other side. We'll get x, y equals y plus 2. We're making a nice little implicit formula now that we can go ahead and take the derivative of. So here's the derivative. And we'll take the derivative of this. So we remember this right here is going to be a product rule. That's first derivative of the second plus second derivative of the first. And we can define x as the first and y as the second. All right, so the first is just x. Derivative of the second, the derivative of y is just dy dx. And I will put a box around it because we will have two dy dx's in this equation. Plus the second, which is just y. And we remember from yesterday when we were just rewriting y, we don't write dy dx because we haven't taken the derivative of it. Times the derivative of x. Well, the derivative of x is just 1. So we don't need to multiply by 1. Equals y plus 2. Well, we'll take the derivative of y. That's dy dx. And the derivative of 2 is 0. So again, I'm not going to write that. All right, so now this is what we're left with. And we can go ahead and rewrite our equation so that all dy dx's are on one side and everything else is on the other. So I'm going to shift this over to the left. I'm going to shift the y over to the right. So I get x dy dx. And then minus dy dx equals, and then I'll subtract the y. Perfect. Now I see I have two terms, each with a dy dx, which means I can factor that out. So dy dx. And when I factor that out, I have an x here minus, since there's no number written here, it's implied that it's a 1. Equals negative, oops, it's not negative, it's just a single negative. Equals negative y, which is just what we're going to leave on the right-hand side. All right, now, of course, the last step is we just want dy dx. So dy dx equals, we can divide the x minus 1 over to the other side. So minus y over x minus 1. And what we were doing yesterday, this would have been an appropriate answer. But we know what y is defined as because it was defined explicitly up here. So we can go ahead and actually plug that in for y so that everything is just in terms of x's. So this is actually minus x plus 2 over x. So this is our y over x minus 1. So I just went ahead and I plugged in y in terms of x's. So now our derivative is equal to this. And this is our final answer just in terms of x's. All right, this is about the same thing. It's just giving you slightly different notation. So it's saying find the derivative with respect to x of the inverse of f at y equals 1 if f of x is x, the fifth root of x. So first of all, I think I've mentioned this before, but in calculus, we don't like to play with roots. They don't help us very much. So what we're going to want to do first of all is going to be to convert this to a fractional exponent. So as a little reminder, we have the nth root of x to the m, and we want to convert this to a fractional exponent. Then this will turn into x to the m over n. In my little way of thinking about it, I think about it as x to the power over root, where the power is obviously just the exponent attached to the variable, and the root is going to be the actual root of our radical. All right, so this is how we're going to convert from a root to a fractional exponent, because once we do that, we can just use our regular old power rule. All right, so first of all, I'm going to rewrite this as y, and I'm going to rewrite this as a fractional exponent. So y equals x to the power. Well, there's nothing written, so it's an implied 1 over root, which is 5. All right, now that I've rewritten this, I can go ahead, first of all, and find the inverse, because I can't take the derivative of the inverse if I don't know the inverse. So inverse. The inverse just means flipping all x's and y's, and so this becomes x equals y to the 1/5. But we're looking for the derivative of the inverse, and so let's take the derivative. And again, we'll just use implicit differentiation. That helps us get some practice as well. So the derivative of x is just 1, and the derivative of y to the 1/5 is using the general power rule. So take the exponent, multiply it to the front, so that's 1/5. Y to the, take your exponent and subtract 1. And the reason why I wrote it like this is because we're going to need to use some knowledge on fractions to actually simplify this. So I'll pull it off to the side. 1/5 minus 1 is the same thing as 1/5 minus. Well, I need to create a common denominator. So the denominator that we're going to want is a 5. 1 can be written as 5/5. 1 minus 5 is going to be -4/5. So 1/5 minus 1 is going to be -4/5. So this tells us that 1 equals 1/5 y to the -4/5. All right. But we notice that I've forgotten something. When I took the derivative of y, I needed to consider that this is y in terms of x. So when I take the derivative, I multiply by dy dx, and I multiply by dy dx. If you ever get to this point where you don't have that written down and you look at it and you go, I'm just solving for y, that's so weird. It's probably because you're missing something. It's probably because we forgot to write a dy dx. Because now we can just go ahead and solve for that. So I can go ahead and multiply the 5 to the other side, divide this y to the other side, and we can say dy dx equals, multiply by the 5, I get 5, y, I will rewrite it like that after. I'll show you why I'm going to rewrite it the way I do in a second. So 5 over y to the -4/5. I might want to rewrite this just because I don't love negative exponents. So I know that I can change the place a variable is in a fraction by negating the exponent. And so I can actually rewrite this as 5y to the +4/5. And that's the same exact thing. Now, I was looking to evaluate this at y equals 1. Evaluate it at y equals 1. So again, this is the evaluation bar at y equals 1. That just says to plug in 1 into our little equation here and see what we get. So this is 5 times 1 to the 4/5. But 1 to literally any power whatsoever is just 1. And so our answer is just going to be 5. So the derivative with respect to x of the inverse here at 1 is just 5. All right, this is just a little recap of what I mentioned. Let's see where, right here. This is the power rule for fractions. So this just says if you have a fractional exponent, you're going to do the same exact thing that you would normally. So you're going to bring this down, and then you're going to want to subtract 1. And that works for any fraction whatsoever. It could be 1 over something. It can be 10 over 7. It could be whatever you'd like. Pretty much the power rule will work with any real number. So you don't necessarily have to write this down. We've been working with this the entire time. All right. Let's see here. This is just a little bit of practice using fractions now. So this is kind of taking a step back from inverses and everything like that. This is just find the equation of a tangent line using the power rule and fractions. So this will be a real quick example. So we again remember that y minus y1 equals m times x minus x1 is the general equation of a line that we're going to want to be using here, where m is going to be the derivative. So we can go ahead and find the derivative. We'll say y prime is, well, the derivative of this is using the power rule. Take our exponent, multiply it by the thing out front. The thing out front is just 1. So this is 2/3 x to the 2/3 minus 1. Well, this is where I'll pull this off to the side. 2/3 minus 1 is equal to 2/3 minus. I want a common denominator. That means that we have to have 3/3 because 3 divided by 3 is 1. Now I can write it over 3 and just combine across with our numerators. So 2 minus 3 is -1. And so this is the same thing as 2/3 x to the -1/3. Now it might also help to rewrite this using a positive exponent because we are looking to plug it in at a specific value. And I'm gonna gather, I'm gonna say that we probably don't know how to plug in things with negative exponents, but we do with positive exponents. So let's rewrite this using a positive exponent. So that means that I can take this, which is technically in a numerator here, it's technically attached to the 2. I can write this in the denominator and change this negative to a positive. So I'm going to rewrite this as 2 over 3x to the positive 1/3. All right, now I can go ahead and say I'm looking for this at x equals 8. So I can plug in 8. So this is 2 over 3 times 8 to the 1/3. But this is still kind of confusing. When you see 1/3, sometimes we don't recognize exactly what this is asking. So what I'm going to suggest is that we try to make this into a root, and maybe that helps us recognize what this is. 8 to the 1/3 equals, well, if we remember that idea that the nth root of x to the m equals x to the m over n, or just the idea of this is the power over root, I know this is some sort of a root. Well, the 1 is the power, and the 3 is the root. And that's exactly what this is saying up here. So this is actually asking for the third root of 8, which, if you remember from your algebra rules, says that you need 3 of some number under the radical to be able to pull it out from under the radical. And in fact, 8 you can write as 2 cubed. And so therefore, the cube root of 8 is just going to be 2. And so this is 2 over 3 times 2, which when you cancel out your 2's is just 1/3. All right, that's just a little reminder of how to use the power rule and some practice with using some fractional exponents. All right, now let's get back into looking at derivatives, but now we're going to shift gear. So we're now not talking about finding the derivative of the inverse of a function. We're looking at the derivative of an inverse function. So you notice the language is slightly different when I say this. So we see, note, to find the derivative of an inverse trig function, what we want to do is we want to apply the trig function to both sides and cancel out the inverse trig function, then use implicit differentiation to solve for the derivative. So this is what I mean. There are general formulas that tell you that the derivative of an inverse sine function is just, and it'll give you the answer, right? That's not how we're going to use this. And in fact, if I give you a question like this on an exam and I say, find the derivative of this function, and you just pull out of thin air this formula, that's pretty much no credit because we have a way to actually solve it, and it's not very difficult. We don't know the derivative of an inverse trig function, but we know the derivative of a regular trig function. So my first suggestion is maybe rewrite f of x as y if you're not given that. So we can say y equals arc sine, this is read as arc sine, sine to the -1 of 3x to the 5th. And I will remind you that this -1 is not an exponent, so you cannot say that this is equal to this. This is not true. This is not a negative exponent, whereas something like sine squared of x does in fact equal sine of x squared. All right, so just be aware of this fact. If it's a -1, this is an inverse. To get rid of an inverse, we can just apply the original function, which means that if I take the sine of both sides, well, inverses get rid of the original function. When you take the inverse of a function, they go away, and you're just left with, in this case, the argument of the function. So what this tells us is that the sine of y equals 3x to the 5th. So this is how you're going to want to approach any of these types of questions. If you see an inverse trig question, you're going to want to take that trig function of both sides, and then that cancels out the inverse trig function. And we know how to actually differentiate regular trig functions because we did a whole lecture on that. Now this is implicit because we have a y inside of our argument, and we can just go ahead and take the derivative. So the derivative of sine, this is going to be a chain rule. So derivative of sine is just cosine of what's inside of our argument. But then because it's not just x, we do need to take the derivative of what's inside and multiply it by what's by that thing. Well, the derivative of y is dy dx. It's 1 dy dx. So I'm going to multiply that by dy dx. And the derivative of 3x to the 5th is 15x to the 4th, using our regular old power rule. Therefore, dy dx equals, I can just divide my cosine to the other side, so that's 15x to the fourth over cosine of y. But we know what y is. We have y equals the arc sine of this thing. And so our answer is actually 15x to the fourth over, and I know this is going to look ugly, but that's just the answer. Cosine of y, which is arc sine of 3x to the fifth. All right. And there may be a way of simplifying this. In fact, there is a way of simplifying this to make it look prettier. But given the tools that we have at our disposal, this is the answer that we should be getting. If we get a different answer, it may look a little bit sus, right? Unless you show me exactly how this turns into the answer that the internet may show, this is the answer that we should be getting. All right, so dy dx is this answer right here. All right, and this is what I mean. So the inverse trig functions have a bunch of specific formulas. So if you take the derivative of the inverse of sine, this is what you get. And you notice that's not what this is right here. Now, of course, we do have to use chain rule because what we had wasn't just a regular x. So for example, here's 3x to the fifth. So when you actually do this, you would plug in your value for x into x here, but then you would have to multiply by the derivative of that x by chain rule. And so you would still wind up with this 15x to the fourth in the numerator just by chain rule. But this denominator would change because there is a way of rewriting this using some techniques. These are the answers. The homework, I don't believe that I put any on our Lumen homework that would require these answers because I don't want us to memorize them. So I put them here just for us to see, just for you to know that they exist. But I don't want us to use these. I want us to actually solve them every single time we have to. All right, let's try another one. So this one now is slightly harder because we see that we have an x squared and an inverse sine. All right, so we're looking to find the derivative of this thing. I again suggest rewriting any function if it's something of x as y. So we'll start by saying y equals x squared, arc sine of x. And it's important to remember how exactly to apply a function to take the inverse. So you might be inclined to go ahead and apply the inverse or the regular function to get rid of the inverse on both sides. But because we have this x squared here, we can't do that. So we actually have to get rid of anything that isn't just our regular inverse trig function here before we can apply the regular function to get rid of it. So we'll divide this x squared away first. So we'll say y over x squared equals arc sine of x. Now, once we do that, we can apply a regular sine to both sides. So y of sine y over x squared equals the sine of the arc sine of x. And again, when you take the sine of an arc sine, these are inverses, those cancel out, and you're just left with what's in the argument. So this and this go away, and you're left with the sine of y over x squared equals x. We have not taken any derivatives yet, though. We've only rewritten it to make it easier for us to take the derivative of. So now we can actually go ahead and take the derivative. We see for this sign here, we will have to use chain rule because we have something inside of our parentheses. So the derivative of sine we know is cosine. When we take the derivative of a trig function, we just leave the argument alone. But because we left the argument alone, we now have to take that into account outside by multiplying by the derivative of that. This is a quotient, and so we will use the quotient rule. Low d high minus high d low over low squared. So this times the derivative of y over x squared. So the denominator low is x squared, d high, the derivative of y is dy dx. And I'll box that in. Minus high, which is y, d low, the derivative of x squared is 2x, all over low squared. This is x squared, quantity squared. And this is equal to the derivative of x, which is just 1. Okay, now we are looking to find the derivative. So we are looking to get this by itself, which means that we have to go ahead and first maybe move our cosine. So I'm going to bring this up here. So what I might first do is divide the cosine to the other side. So we would say x squared dy dx minus, and I'm going to multiply the 2x by the y, so 2xy over x. X squared squared, a power to a power is when you multiply them. So this is x to the fourth power equals 1 divided by this cosine. So 1 over cosine of y over x squared. Okay. Now, I will note 1 over cosine is actually secant. So this is the same thing as secant of y over x squared. Now, if this was on a test, would you get points taken off for not remembering that? No. But if you do remember that, it does help to rewrite it. So we do still have to solve for dy dx. We'll first start by multiplying this x to the fourth to the other side. And I'm also going to rewrite this as secant so that we don't have a fraction. So I'm going to say x squared dy dx minus 2xy equals, I'm going to multiply the x to the fourth over here, and I'm going to change this into a secant of that same argument. All right, now I can go ahead and add the 2xy to the other side. So I have x squared dy dx equals x to the fourth secant of y over x squared plus 2xy. And then I can just divide by x squared. So dy dx, I suppose I should have left myself more room, but that's okay. Dy dx equals x to the fourth secant of y over x squared plus 2xy all over, what is it, x squared. All right, and the last step could just be everywhere you see a y, you plug in your original function. So I'm going to, sorry for going out of order, I'm going to plug it in over here and just rewrite our final answer. So we have dy dx equals, let's see, x to the fourth secant of, it's y, but it's actually this whole function. So this is x squared arc sine of x over x squared plus, I suppose I haven't given myself enough room, but that's okay. 2x, y is x squared, arc sine of x, and this is all over x squared. All right, if you want to simplify this a little bit, you can. So if you wanted to simplify, technically these x squareds could go away. You can multiply this x by this x squared, and then you could divide out this denominator. And so we could rewrite this as, if we divide this by this is now x squared secant of arc sine of x, and then 2x times x squared is 2x cubed, but x cubed divided by x squared is just plus 2x arc sine of x. So you could rewrite it like that if you wanted to, but you could also just leave it like that. All right, I know this one was slightly more complicated, and I know that I kind of wrote it like a mess, so I do apologize if you had a hard time following along. But that's the gist of if you have a slightly more complicated looking problem from the get-go. All right, this is the last question for today. So now we're going to be taking a look at a tangent function. I know we've only used sine so far. All right, so we will once again want to find the derivative of this. It's written as f of x. I'll start it over here so that maybe you have a slightly better chance of making it look a little bit more lined up. So I'll say y equals arctan of x squared. But in order to solve this, I want to take the tangent of both sides. Because when I take the tangent of both sides, this tangent and this arctan go away, and I'm just left with the tangent of y equals x squared. Because we have in a previous lecture already found the derivative of the tangent of y, I'm not going to make us solve that again. If we have not already found the derivative, I might say, like for say cosecant, we may actually want to go ahead and try to find that derivative. But we know the derivative of tangent is just secant squared, so we can just use that fact. So the derivative of tangent is secant squared of just the argument. So again, we don't touch that, but we do need to take that into account if it's something other than x by multiplying by the derivative of that outside. So the derivative of y is just dy over dx equals the derivative of x squared, which is just 2x. All right, there's only one other step to get dy dx, which is divide by the secant here. So that's 2x over secant squared of y. And then I can go ahead and re-plug back in y. So I'll rewrite y equals arctan of x squared because it looks a little bit tricky here because I just immediately took the tangent of that function. And so this is actually also 2x over secant squared of the arc tan of x squared. And this is going to be your final answer. All right. If you have any questions, let me know. And we have one more lecture before the exam. The exam will cover everything through that lecture, but that lecture is not too hard. It does require paying attention to the specifics of it, of course. But if you have any questions, let me know.